Alrighty, so the last two concepts that we'll have to go over for Unit 7. The first one is atomic orbitals. Now we talked about last time how depending on how much energy the electron has, right, it can be further away or closer to the nucleus of the atom. Now there is a lot of text here, which I will have you guys just read on your own time, because it is in your assigned reading, and I know that all of you definitely read 80 pages from the text every week like you guys are assigned, right? Of course not. Okay, I don't even want to read that. Okay, so one thing that we're going to learn about is electron configurations, okay? And electron configurations are basically a method for us to describe how the electrons are distributed or where they are in an atom or ion. So remember how we said last time they could be in the first shell, or they can be in the third shell. They cannot exist in between because energy is quantized, right? It has to be at a specific level. Now, electron configurations allows us to describe where the electrons are, okay? Now, one thing you guys need to know is that every electron has a different ionization energy. Remember ionization energy? How much energy it takes to remove an electron from the atom. So electrons that are further away from the atom, do you guys think it'll have a greater or lower ionization energy than an electron closer to the atom? Yeah, it's going to have a lower ionization energy, right? So the further away it is, the lower the ionization energy, because the easier it is to steal an electron from that atom. So like if you guys were trying to steal my phone, and then my phone was all the way over there, it's further away from me, it's a lot easier to steal that from me, right? I mean, I'm gonna catch you because I'm a good sprinter, and then I'll jump you and I'll steal your phone. But you get the point, right? The further away something is from you, the easier it is to take away. So the further the electron is from the nucleus, the easier it is to remove the electron. Whereas if my phone was in my pocket, right, it's a lot harder to steal it than if it was like 10 feet away from me. Exactly, yeah. Yeah. Yeah, the easier it is to take. So let me write that for you. So the further the electron from the nucleus, the easier it is to remove. So easier to remove, which means that it has a lower ionization energy, because ionization energy is how much energy it takes. So the further away it is, the easier it is to remove, which means a lower ionization energy. So basically, the higher the shell number, the easier it is to take away, which makes sense. Okay. Now, atoms with multiple electrons, that's what multi-electron means. We can think of them as having shells and subshells. Now, we'll talk about shells and subshells in a second. But when they are in the same shell, they have similar ionization energies. And then there's a term called core electrons. Core electrons are basically all the electrons that are not valence. If you guys remember valence, valence are the electrons on the outside shell. Anything that's not on the outside shell is considered a core electron. Okay. And so when we talk about chemical reactions and ions and stuff, we're usually talking about moving the valence electrons. The core electrons, we don't really think about them very much. They're pretty boring. They just kind of stay in the middle. There's like one type of problem that talks about core electrons. Usually has to do with ionization energy, but we'll talk more about that in the next unit. Okay. So that's pretty much some of the information, the important stuff you need to know about orbitals, at least for this unit. But do you guys have any questions? If you guys want more detail, because I know this is riveting stuff, you guys can read the textbook. Yeah, some people. Just want to raise your hand? All right, for sure. You wanted me to notice you, right? Yeah, notice me, senpai. All right. It is gonna be in the video. I'm not a senpai though, right? Teachers aren't senpais. No, see, it doesn't work. Sensei, I'm sensei. Thank you, dude. Hey man, this shows I'm not watching those slice of life anime anymore. I don't know these terms no more. Anyway, All right, so that's atomic orbitals. Now, all right, moving on. So we're going to be talking about something called quantum numbers. Okay, so Bohr, if you guys remember the dude who contributed a lot to the atomic model, he came up with these numbers to help us describe the electrons in the atom. Now, every single electron has 4 quantum numbers. Okay, and so if chlorine, for example, has 17 electrons, all 17 of them will have a unique set of 4 quantum numbers. Okay. So the first quantum number, we call it the principal quantum number. I'll just let you guys know, even I don't memorize these. I just remember the letters N, L, M, and MS. So you guys can remember it like this. So the first one, the first quantum number, N, can have positive integral values, which means positive whole numbers. It can be 1, 2, 3, and it tells you which shell that electron is in. So like I said, every electron in an atom has a unique set of 4 quantum numbers. The first number, the N number, is going to tell you what shell it's in. Okay. All right. The next number is called the angular momentum number, and it's the letter that represents it is L. It can have integral, which means whole numbers, values from 0 to n minus 1. So for example, let's say we have an electron and it's in the 3rd shell. So n equals 3. Okay, that means that the angular momentum number L can either be 0 to n minus 1. So it could either be 0, 1, or 2, because the max you can get it to is n minus 1. Okay. The third quantum number is the magnetic quantum number. It's M, and it can have integral values between negative L and L, including 0. So if you guys notice, it can be negative L, which is negative 2. So it can have negative 1, 0, 1, and 2. Basically, negative L to L. Okay, and I know this is kind of weird right now, but it'll make more sense once we start just using these to describe various electrons. It's not too difficult. Okay, and then the last one, the electron spin quantum number, MS, it can have a value of, it's always going to be positive 1 positive half or negative half. Doesn't matter what the N, L, and M are, it's either going to be positive half or negative half. And that just kind of tells you which way the electrons are spinning. Okay, so those are the 4 quantum numbers that every electron is going to have. Every electron is going to have a different set. Okay, so they might have the same N, L, and M, but then that means the MS has to be different. Or it could have the same N and MS, but then the L and M would have to be different. Okay, so you can't have all 4 of them the same for different electrons. Okay. And we just use this to describe where the electrons are in the atom. Okay. Any questions about any of these 4 values? Okay. Yeah, what's up? Oh, this right here? Oh, it should be negative L. Yeah, sorry. Let me see if I can get in a cursive font or something like that. What font do you guys want? Oh, lobster. That doesn't help. Pacifico. Oh yes, there we go. Pacifico is the way to go. All right, a little better. All right, yeah. Okay, Pacifico. All right, so I'll give you guys 20 more seconds to copy that down. Not much more to say about it. We're gonna learn how to use these in just a second. So if you guys have the notes up on Canvas, you guys can scroll down to the next page and you'll see this big Unga Bunga chart. And I'll show you guys what that means and how to use it. Okay. All right. go down to this chart. All right, so this chart right here is what we use to describe every electron inside of an atom. Now, as you go higher and higher, the energy in the electron is going to get higher. That's why there's a big up arrow. And these represent basically how far an electron is from an atom. Okay, so I think the easiest way to talk about this is just by picking an element and then starting to draw the electrons in there. Okay, so let's go to the periodic table. So you guys have one in front of you? No, right? Sorry, let me pass it out. Okay, but we're gonna go to the periodic table and we're gonna pick an element that we want to describe. Okay, so you guys want to? Well, we'll take a vote. Anybody have an element that they like, preferably in the first 3 rows? Carbon. Carbon. Okay, let's do carbon. Everybody's favorite carbon. Carbon. All right, so everybody find carbon on their periodic table. Nitrogen. We could do nitrogen now. Nah, nitrogen is too close. Let's do carbon because carbon is what allows us to live. And we are all organic compounds. If there's extras, you can just leave it like on a seat behind you, next to you, whatever. As long as you have one. Yeah.
So are we gonna have to write all the arrows?
Yes. I'm never gonna have you do that on the test. You just need to know how to interpret it and to solve it.
That's what they did on the final test.
Maybe I should do that too then. Okay, so let's do carbon. So everybody take a look at carbon. Okay, carbon is right here. Now we can derive some information from carbon just by looking at it on the periodic table. So carbon is right here. So let's look at carbon. How many electrons is neutral carbon gonna have? Yeah, 6. The number on the top tells us the number of protons, right? So carbon has 6 protons. And so if we're talking about a neutral carbon, it means it has 6 electrons as well, okay? Should be pretty simple. Now we're gonna learn how to use some other information on the periodic table. If you guys take a look at carbon, which row is it on the periodic table? Second, rows go side to side. So carbon is on the second row, right? So if carbon is on the second row, that means carbon is gonna have 2 shells. Okay, so the highest N number for electrons in a carbon atom is gonna be 2. So depending on which row an element is in on the periodic table, that will tell you how many shells it has. Now there are some exceptions. And we'll talk about them, namely these guys right here in the middle. We'll talk about that in our next example. But typically, the number of rows an element has, that tells you how many shells it has, okay? Okay, so we're gonna go off that for now, okay? So 6 electrons and 2 shells. Okay, so if we go back to our big chart, we said that carbon has 6 electrons. So what we're gonna do is we're gonna fill in this chart, these lines, using electrons. Now you'll probably have to have this on your paper, but don't copy this all out at one time. Just know how to fill this in based on these problems that we do, okay? So one of the rules we always need to start with is that we always want to start with the lowest energy levels, okay? We're gonna start with lowest energy levels, okay? And so if we take a look at this, the lowest energy level is 1s. Okay, so we're always going to start by filling in the lowest. Okay, so carbon has 6 electrons. So the way that we describe electrons is with these arrows like this. And so we're going to go 1 arrow, 2 arrows. So that's 2 electrons. Okay, we're going to jump up to the next energy level. We're at 2s. So we're going to fill that in 3, 4. And then now we have to go to 2p. So this is where the next rule comes in. The next rule is that we want to fill up the empty subshells first, okay? So we're gonna fill in empty energy levels first. Okay, then we can start putting in and pairing the electrons together, okay? So carbon has 5, 6, and so we want to do it like this, okay? Okay, now this might be a little bit weird, but we'll go over a couple more examples. But this also connects with what we learned about the LM, NLM, and MS. Shit, I was doing the regular alphabet. Yeah. Okay, so if you guys take a look at this, the number 1 and the number 2, this is going to tell us the N. Okay, the shells, which shell it's in. So like we said, carbon only has 2 shells. So the highest number for N that we can have is 2. Now the next number, the next subshell is denoted by this right here, S and P. Okay, these tell us the subshell. So these are the L values. Okay, so there's an S subshell and there's a P subshell. Okay, so these are your L values. Okay. And then if you guys notice, inside every subshell, there's a different set of lines, right? In the 2p subshell, there's 3 lines. In the 2s and 1s, there's 1 line. And these tell us the M value. Okay? These are the M's. Okay? These lines are the M's. Okay, and do you guys notice how one of the arrows is pointing up, one of the arrows is pointing down, right? This tells us the spin of the electrons, the ms value. So it could either be spinning up, +1/2, or it can be spinning down, -1/2. Okay, so this is a way for us to kind of visualize where the electrons are, what they're doing, which subshell they're on, etc., etc. Okay. Alrighty. I know it's a little bit confusing, but do you guys have any preliminary questions? We'll do a few more examples just so you guys get comfortable doing this. Yeah, what's up, great. These are like how we put the arrows in there. Yeah, of course. So we said carbon has 6 electrons, right? And so what we want to do is we want to start filling in these lines so that we can see where the electrons are inside the carbon atom. So we only have 6 to work with, so we can only draw 6 arrows, okay? The first rule is we start with the lowest energy level, and so we've got to fill up this 1s. So we draw 1, 2 electrons. Okay, now this guy is filled up. There can only be 2 electrons per line. Okay, we move up to the second, to 2s, and then that's where we draw 3 and 4, because we need to fill that up. Then we need to move up to the next energy level, 2p, and this is where we have to draw number 5 and number 6. And the reason why we separated them is because we want to fill in the empty ones first, and then we go back and then start filling in pairs. Yeah.
Okay, just
For
3D, does it just go down to the transition metal?
Yeah, we're going to talk about transition metals in a few problems. So yeah, hold off on that one. We'll go over that in a sec. All right. Any other questions right now? Okay. So what this actually tells us is it allows us to write something called the electron configuration for an atom. Okay. So the electron configuration for carbon, what we want to do is we want to just write these shells. We're going to write 1s. So 1s, and then there's 2 electrons in the s subshell. So we write 1s and then exponent 2. We go on to the second one, the second energy level. It's going to be 2s, and there's 2 electrons in there. So it's 2s, 2. And then after that, we have 2p, and there's 2 electrons in there. So it'll be 2p2. Okay. So the electron configuration for carbon is 1s2, 2s2, and 2p2. So basically, this is how we can communicate where the electrons are. We got 2 electrons in the 1s subshell. We got 2 in the 2s subshell. And then we have 2 in the 2p subshell. Okay. So I know this might be a little bit weird, but again, we're just describing where the electrons are inside of the atom. Okay. All right. Yeah. What's up? Huh? Oh, if we drew a picture of it, we're actually going to get to that at the end of the lecture. Yeah. You guys are just jumping ahead of me today. All right, let's do another problem just so that we can kind of start practicing. I'll do this one with you again, but if you feel confident trying this on your own, you can go ahead and try finishing it up. Let's do one that's a little bit bigger, okay? Let's do calcium. Okay, we're gonna do calcium. Ca. Now, if we take a look at calcium, we're gonna notice that calcium is right here. So how many electrons does neutral calcium have? 20, same number as the protons, okay? So we actually don't even need to look at the shells. Let's just start by filling in the electrons. Now we want to start with the lowest ones first. So let's start with 1s. Okay, so we're going to draw 1, 2. We're going to move up to the next energy level, 3, 4. And then we're going to go to 2p, 5. And then we want to do the empty ones first. 6, 7, and then we go back and pair them up. 8, 9, 10. Move up to the next energy level. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And that's how you would fill it, the electron, excuse me, that's how you'd fill in the electrons for calcium. So you just need to go from the lowest to the highest or higher up by filling in the electrons, okay? And this basically tells us where the electrons in the calcium atom are going to be hanging out. So if we wanted to write the electron configuration for calcium, am I moving a little too fast? No, okay. If I wanted to write the electron configuration for calcium, we would start from the bottom. How many electrons are in the 1s subshell? 2, so we would write 1s2. How many are in the 2s subshell? 2s2. And then how many are in the 2p? 2p6. We have 2 in the 3s. We have 6 in the 3p. And then we have 2 in the 4s. So the electron configuration for calcium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now, that's a lot to write, right? So that's the electron configuration. And that's a lot of writing. And so, because chemists are really lazy, they found that they made up another way to write the same thing, but to do it shorter, okay? And we call this a noble gas configuration. Okay. So noble gases are elements that are on the far right of the periodic table, right? They're known for being stable. They're kind of like loners. They don't want to do anything with anyone else. Because they are happy the way that they are. They don't want to move electrons around. So what we do is we look at the noble gas that comes right before calcium. So if we look at calcium, calcium is number 20. So if we go backwards, which one is the noble gas right before calcium? Argon, right? And so argon, so what we're going to do for the noble gas configuration is we're just going to write argon in brackets. And argon, if you guys notice, is going to be one. It's basically this is argon. Okay, 1s2, 2s2, 2p6, 3s2, 3p6. That's argon. So we just write 4s2. This is a noble gas configuration because the AR in brackets basically tells us everything else before we get to calcium. So hopefully that helps us understand how to fill out these electron levels. Now there is an easier way to do this, to find the electron configuration and to find the noble gas configuration than filling in these filling in these lines. Yeah. Sorry, what was that? Yeah, argon is the noble gas right before calcium because calcium is number 20, right? So if we go backwards on the periodic table, 19 is potassium and then argon is 18. Yeah. Okay, so I'm going to show you guys now how to do the electron configuration without doing this big chart thingy, okay? Okay, so if you guys look at your periodic table, and if you guys want to take out the periodic table from the sheet protectors and kind of just keep it for yourself, you guys can by writing this down on the periodic table. That way you don't need to copy this in your notes. But if you look on the periodic table, every section on the periodic table has their own area for the subshells. Now we talked about S and P, right? So let me just kind of refresh real quick. So we said the N number, the shells, right? Okay, the shells are going to depend on what row that element is on. So nitrogen is on the second row, so we'll always have 2 shells. If you look at rubidium right here, it's in the 5th row, so it's going to have 5 shells. Okay, the next one we said are the subshells, and subshells are basically going to be the S, the P, the D, and there's an F orbital. Okay. Those are the subshells. Okay, let me show you guys where they are on the periodic table, okay? So this entire section right here, the first 2 columns, these first 2 columns represent the S subshell. Now the only exception is helium. We have to pretend helium is right here. Okay. Including helium, everything in the first 2 columns are the S subshell. So if you guys notice with calcium, what did we say calcium's final electron configuration was? We said it was 4s2, right? And so if you look at calcium, it's in the 4th row, right? 4. It's in the S subshell because it's in the first 2 columns. And then it's the second box in the S subshell. So that's where we get the 2 from. Okay, so just to repeat, this is a lot easier, right? Calcium is in the 4th row, so that's where we get the N number 4. S is the L, the subshell. It's in the S section. And then if you look at calcium, it's box number 2 in that subshell. And so that's why we have 2 for the subshell. Okay. So these first 2 columns represent the S subshell. Oh, let me see if I can get a thicker pen. Oh yeah. Got S. All right, let's go to P now. Now P is going to be on the other side. You guys might have been able to guess that. But P is going to be on this side. We typically don't look at the bottom row because those are all man-made synthetic elements. But you guys can just kind of think of the entire right side as the P subshell. Okay, so everybody on this right side are the P subshell. Okay, so if we look back at carbon, right, we said that carbon was what? 2p2, right? We said carbon was 2p2. That was the last one, which makes sense because carbon is in the 2nd row. So it's in the 2nd shell. It's in this P, what's it called? Subshell. And then it's the 2nd box in the P subshell, which is why it's 2p2. Okay, and then nitrogen is 2p3. Oxygen is 2p4, right? And then neon would be 2p6. So it's a very easy way for us to figure out where the electrons are inside each element. Okay. All right, next we're going to look at the D subshell. And the D subshell is this middle area right here where the transition metals are, okay? So all these guys are going to be the D subshell. Okay, now the D subshell is weird because the subshell number for D will always be lower one value lower than the row that it's in. Okay, so what do I mean by that? If you guys take a look at calcium, right? We said that calcium is in the 4th row. That's why the N number is 4, right? So can I erase this part right here? Okay. So if we take a look at calcium, let's review calcium. We said calcium is in the 4th row, right? It's in the 4th row. That's why it has 4 shells. So that's why we end at 4s2. Okay. However, if you guys take a look at iron, okay, iron is in the same row, right? It's easy for us to be like, hey, iron is in the 4th row. It's in the D section, so it's going to be 4D, 1, 2, 3, 4, 5, 6, right? That's incorrect. Okay, iron is in the middle. So like we said, everybody in this transition metal area, so the transition metals for the D subshell, it's always going to be one number lower. So iron is not going to be 4D6, it's going to be 3D6. And the reason why is this middle section right here, the D subshell, the D subshell actually has a lower energy level than the S subshell that it's on the same row as. Okay, kind of a weird reason, but it's just something that you'll have to know. Just remember, and they will try to trick you with us on the AP Chem test, like guaranteed. Just know that iron, since it's in the D subshell, it has to be 3D6 and it has to be 4s2. So it's going to fill in the 4s2 and it's also going to be 3d6. Okay, so the D subshell is a little bit weird. Yeah, so iron is in the D subshell, right? Basically, if we have something, so normally we say if it's in the 4th row, the N number has to be 4, right? Same as the row number. However, for the D subshells, we have to subtract one value from the D. So instead of being 4D6, because it's in the 4th row, it has to be 3D6 and 4s2, because it needs to, we need to subtract one number from the D subshell. And if you guys take a look at the chart, it also has that too. If you guys notice, the 3D is a little bit higher than 4s. It should actually be a little bit lower, but basically we want to fill in the 4s and then go to 3D, okay? And then 4D is in between 5s and 5p. Okay, if you notice 3D is between 4s and then 4 is between 5. So the D subshell is always just one lower than the row that it's in. Okay, and then the last one, you're not going to see this very often ever, and it's going to be the F subshell. The F subshell are these guys on the very, very bottom. You are very rarely, if ever, going to see these. But these are that's how you count for the F subshells. Okay. All right, so if you guys wanted to draw this on the periodic table inside those sheet protectors, you guys can take it out and take them home. I don't really mind, but just know those are the subshells. And this makes it a lot easier for us to figure out the electron configuration for different elements. Okay. Any questions? You guys feel a little bit more confident doing these, hopefully? All right. So if we are good, we actually did a bunch of the ones that are on the workbook. We did 7.6, 7.7, 7.8. So let's do 7.9. I want you guys to write the electron configuration and noble gas configuration for iodine. Okay, so I'll leave this up here, but I want you guys to find the electron and noble gas configuration for iodine. The electron configuration is kind of long, so I apologize in advance, but just write the noble gas configuration for iodine. All right, maybe 30 more seconds. I know the electron config is kind of long. Alrighty, guys. So if you're finishing up, feel free to finish up, but I'm gonna start going over it for the sake of time. So we're gonna do the electron configuration for iodine. So let's do iodine. Iodine is right here. So we can just start off with the first two. The first two is 1s and 1s2. So that's gonna take these guys out. We're gonna go to the next one. This is the second row. So 2s, and there's two of them. So 2s2. We're going to go to the p suborbital in 2. So 2p, 1, 2, 3, 4, 5, 6. So it'll be 2p6. You guys kind of get the point from there. We got 3s2. We got 3p6. We have 4s2. Now we have this section right here. It's going to be the D subshell. Is it going to be 4D? 3D. It has to be 3D, and if you count them, there are 10. And then we have to go to 4P, and then there's going to be 6. Almost done. We have 5S2, and then here we have 4D, 10, and then for iodine, we're finally at, 5, my bad. 5P, 1, 2, 3, 4, 5. So 5p5. So this is going to be your electron configuration. That's about as hard as it's going to get. And that's about as long as it's going to get. Okay. Any questions? Well, not too bad. Okay. I also asked you to do the noble gas configuration. For the noble gas configuration, we need to go backwards. What's the closest noble gas behind iodine? Yeah, krypton all the way back to here. So we're going to do Kr in brackets, and then we have to do 5s2, so 5s2, 4d10, and then 5p5. That's going to be the noble gas configuration for krypton, because krypton basically explains everything from 1s2 until 4p6, because if you look at krypton, krypton is 4p6. So that's why we can just put krypton in there to describe iodine. Okay. And that's pretty much it. Yeah. Yeah, so we just need to look at the noble gas that's behind it, that's closest. So if you look, iodine is right next to xenon, but the closest one behind it is all the way back here where krypton is. So we just replace everything that krypton can explain. That's basically everything from 1s2 to 4p6, because krypton is at 4p6. And then we just write 5s2, which is right here, 4d10, which is right here, and then 5p5, which takes us to iodine. Okay, so there are very rarely, but there are some questions that will try to trip you up. Okay, so let me just erase this real quick. So we said iodine, the noble gas configuration is Kr, 5s2, 4d10, and then 5p5. Okay. So there are some questions where they try to trick you and they ask you, what's the electron configuration for I minus? Okay, so let's think about this. If there's a negative charge, did I gain electrons or lose electrons? You gained electrons. So we need to fill up electrons in the outermost shell, right? The subshell. So that means that for I minus, what happens to this value right here? It increases. So it's going to be 5p what? 5p6, correct. So we can write this as this, or we can write it as what noble gas does it become like? Xenon. It becomes xenon. Okay, so I minus can be this krypton 5s2, 4p10, 4d10, and 5p6, or it can basically just be xenon. Okay, so there are some times where they will try to trip you up and give you an ion where you have to add and remove electrons. But just remember, just add it to the final subshell or remove it from the final subshell. Okay. All right, any questions? All right, so that's electron configuration. This is actually going to kind of carry us over into the next concept, which is the last one we're going to go over for this unit. Okay. All right. So the last thing we're going to go over for this unit are going to be shell models, where we're actually going to draw the electrons now. Okay. So again, just to review, atomic structure, protons and neutrons are in the nucleus, and the electrons fly around in that empty space around the atom, and we call that the electron cloud. Okay, electrons are constantly flying around the cloud, but we said that there are areas where they like to hang out, right? Those are the energy levels because it's quantized energy. And so electron shells, they're basically visual representations of where the electrons are most likely to be. Okay, now I do want to remind you guys that electron shells aren't real. Electrons don't orbit around the atom like planets revolve around the sun. We just draw it like that because it's a lot easier than trying to draw all the subshells and things like that, because then we need to go 3D and can't really draw 3D on a piece of paper. Okay, so what we're going to end this class with, or this unit with, is drawing shell models. So if you had me or Mr. Pepic, I don't know if, I think Mr. Edwards does this too, but you should know how to do these already. It's drawing shell models for the atom. Now, there are 4 rules that you guys need to keep in mind. The number of shells an element has is the row number. Okay, we just talked about this. Okay, the maximum number of electrons in each shell is equal to the number of boxes in each row. So what I mean by that is, if you guys take a look at the periodic table, how many boxes are in row number 1? 2. That means you can only draw 2 electrons in the first shell. How many boxes are in the second row? Yeah, 8. So it's going to be a maximum of 8 inside of the second shell. Okay. Okay, we want to fill in the shells from the inside out, right? Because electrons like to fill in the lower energy levels, just like how we learned with the configuration. And then if there are no electrons in a shell, the shell does not exist. Okay, so if I take out an electron and then the shell on the outside disappears, it doesn't have that outer shell anymore. Okay. All right, so those are 4 rules that you guys can keep in mind, and we're just going to jump right into examples. Okay, so I'm going to do helium and carbon with you guys, and then I'm going to have you guys try the next 2 on your own. Okay. All right, so let's look at helium. Okay, so helium is in which row on the periodic table? 1. Yeah, it's in the first row, right? Rows go side to side. So helium has 1 shell because it's in the first row. Okay. And then helium, if you guys notice, is the second box in the first shell, right? So we just need to draw 1, 2 electrons. 2 electrons in the first shell, and that's it. That's what helium looks like. Super simple. Okay, let's do carbon now. If you take a look at, if you look at carbon, which row is carbon in on the periodic table? Second row, yeah. So for carbon, we would just draw 1, 2 shells around it because carbon is in the second row. Second row means 2 shells. And if we look, we have to fill in the electrons from the inside out, right? We said the first shell can only hold 2 electrons. So we have to draw 2 electrons in the first shell. We look at carbon though, it's box number 1, 2, 3, 4. So it's going to have 4 electrons in the valence or the outermost shell. So these are the shell models for helium and for carbon. Okay, so not too bad. With the bigger atoms, you guys can kind of see how this will become a pain in the butt. But that's basically how you do it. Okay, so I'm gonna give you guys about 2 minutes, 3 minutes. I'll give 2 minutes. I'll give you guys about 2 minutes to do 712 and 713. I want you guys to draw the shell model for sulfur, and then just to kind of pick your brain a little bit for Be2+, beryllium's most common ion. Okay, light work. Okay. Okay, so take a second to draw a picture of sulfur shell model and beryllium shell model. Be2+, sorry. Be's MCI. It's okay, guys. You guys have seen my drawings. Same. What's over there? Alrighty, guys, I'll give you another minute to finish up, and then we'll be all done. Yeah, it can hold up to 8. It doesn't have to have all 8, but it can hold up to 8. Yeah. Alrighty, guys, let's go over these two, and then we will take a quick break, and then we will finish up with the last concept, which is personally my favorite, because it's the least amount of drawing. Okay, so let's do sulfur. Sulfur is pretty easy. How many shells does sulfur have? 3. Yeah, it's in the 3rd row, so we have 3 shells. Okay, and then from there, we know that the first shell can hold 2 max. So we draw 2. Second shell can hold 8. Sorry if this is hard to see, guys. Let me know if you want a better picture. And then for sulfur, if you guys count the boxes to sulfur in the 3rd row, it's 1, 2, 3, 4, 5, 6. So you'll have 6 electrons in the outermost shell. Okay. And so one thing I do want to mention is, we talked about this before, but the outermost shell of an atom is called the valence shell. Okay. And so how many valence or outside electrons does sulfur have? 6. So sulfur has 6 valence electrons. Okay, so just keep that in mind. It's a term that gets thrown out a lot, so just make sure you guys are comfortable with it. I know we've talked about it before, but just wanted to remind you. Valence just means outside. And so sulfur has 16 total electrons, but it has 6 valence electrons, okay? And 10 core electrons because the inside ones. All right, let's do Be2+, and this is the one that I kind of threw out here just to trick you guys up a little bit. But let's do beryllium 2+. Okay, so if we think about regular beryllium, okay, how many electrons does regular beryllium have? 4, right? It has 4 valence electrons. So if I have Be2+, how many electrons does that have? 2. Okay. So if you look at beryllium, beryllium has 2 shells, right? So I'm just going to start off by drawing 2 shells. Okay, but beryllium only has 2 electrons. How many electrons go in the first shell? 2. So if we draw 2 electrons in the first shell, do I have any more to work with? No. So do I have a second shell? No. So beryllium only has, or Be2 plus only has 1 shell with 2 electrons, okay? So if you guys notice, what element does beryllium look like? Yeah, it looks exactly like helium. Okay, the only difference is that in the nucleus, beryllium has more protons. So Be2 plus is actually smaller than helium because there are more protons, which pulls the electrons in tighter. We'll talk about that next unit, but just keep that in mind. All right. Any questions on that? All righty, guys. So I'll give you guys about a 7-minute break. You guys can stretch your legs, go to the restroom, and then we'll come back and then we will finish unit number 7. All righty, guys. So we're actually going to finish up with something related to shell models. So if you guys noticed, if we start drawing bigger elements, shell models get really annoying, right? So for example, let's take a look at barium, okay? How many shells does barium have? It's down here. 6. So if I asked you to draw barium, you would have to draw 1, 2, 3, 4, 5, 6 shells. And how many electrons will you have to draw? Yeah, 56, which is basically a trillion, right? So nobody has time for that. So instead, a bunch of very smart people said, hey, let's draw Lewis structures. And so in Lewis structures, we only draw the valence or the outermost shell. Okay. And this is very helpful because valence electrons are the ones that are involved in chemical reactions anyway. And because the core electrons don't really do much. And so what's the point of drawing stuff that doesn't do anything? We want to draw the ones that are interesting and do the reactions. So these are the rules for drawing Lewis structures. Very easy. You just basically count boxes in the row to determine the number of valence electrons. You want to draw the electrons clockwise. And then we'll ignore groups 3 through 12 for now, which is basically transition metal area. Okay. So we're going to draw argon and radium. Okay. Okay. So argon is right here. So for our Lewis structure, we're going to do argon and radium. All we need to do is count the boxes in that row, and then that'll give us the valence electron. So argon is in the 3rd row, right? So let's count. We have 1, 2, 3, 4, 5, 6, 7, 8. So argon has 8 valence electrons. That's it. That's how you draw Lewis structures.
Wow.
Yeah, it's stupid easy. Okay, let's do radium now. Radium is down here. How many valence electrons does radium have? It's in box number 1, 2. So it's going to have 2. That's it. Okay, the key thing is that we're going to ignore this middle area, at least for now. We're going to skip the transition metals. Okay, so if I asked you to draw the Lewis structure for iodine, what we would do is we go 1, 2, skip, 3, 4, 5, 6, 7. So iodine will have 7 valence electrons. All right, and that's pretty much it. That's how you draw Lewis structures. Any questions? Yeah, unit's over. I think that is the unit. It's not? Is there more? Dang it. Oh, dang it. There is more. Ugh. Okay. Why did I make this so long? Okay, so we're going to do 2 more examples, 16 and 17. Thank you guys for reminding me. Okay, 16 and 17, and then we'll be done. I want you guys to try this out. So we have K plus and Al3 plus. Now I want you guys to draw the Lewis structure for these. It's going to be a little bit trickier, but I want you to draw the Lewis structure for K plus and Al3 plus. If it helps, you can try the shell model first, but you want to get comfortable drawing the Lewis structures without the shell model.
so easy that it makes it like
See, but then that means it's not easy. Sure. What is that? Can you just show it to me? I'm scared. Wow, pretty good.
No, look at what it says.
No. No ghost. Ghost what?
No,
Hello?
faces a lot.
Ghost fixes?
Faces.
Ghost faces.
His name is
allowed.
Ghostface. And then he says that face.
Oh.
And he
Oh.
constantly in his head face now?
Interesting. I don't get the joke, but okay. Ha 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 ha. Okay,
Last year.
you guys ready to go? No? Still
Yeah,
working on it?
I would say.
Okay, I'll give you guys 30 more seconds to finish it up. Alrighty, guys. So let's go over these and then we will be all done for today. I guess we could finish up a little early. Okay, we're gonna start with potassium first. So if you guys take a look at regular potassium, how many shells does regular potassium have? 4, right? It's in the 4th row. Okay, how many valence electrons does potassium have? 1. So potassium, regular potassium has 4 shells and 1 valence electron. Now, if you guys take a look at K+, did it gain or lose electrons? Yeah, so that means that when we go from K to K+, we lose 1 electron. Okay, we said that potassium only has 1 valence electron. So if we get rid of the valence electron, do we have anything in that valence shell? No. So if I have nothing in that valence shell, that means that 4th shell disappears. Now the 3rd shell becomes the new valence shell. And so how many electrons did potassium have in the 3rd shell? It had 8. Dude, don't speak Spanish, man. I got real confused real quick. I was like, what number is that again? So yeah, K+ is going to have 8 valence electrons and it has 3 shells. Okay, regular K has 1 valence electron and 4 shells. Okay, so just keep that in mind. All right, and then last one, aluminum. Since aluminum lost 3, right? Aluminum had 3. If we go 3, 2, 1, those disappear. Al3+ is going to have 2 shells, and it's going to have 8 or whatever valence electrons. Okay, 8, right? 8. Okay. See, I know Spanish. I didn't fail Spanish 3. Dude, I'm telling you, it's so supernatural, man. How does one pass AP Chem and Physics but fail Spanish 3? Anyway. Yep. Yep. 4 on the AP Chem. I think a 3 on the AP Physics. AP Physics did not make sense, man. The last question was legit. Like there was like a nuclear explosion underwater, which propelled like a something gram bullet through like through the water, and then it passed this sensor like 50 meters away. The density of water is 1 gram per milliliter. So I calculate the energy that was released from the explosion. I was like, okay.
When would this ever happen?
I don't know. But anyway, that's pretty much it for unit 7. So congratulations, guys. We'll be taking unit 6 and 7 exam the Monday we get back. So just make sure you guys are prepped for that. Next time I see you, we'll do some practice problems, or you guys can work on your homework as well. Okay?
No story, nothing, no like additional steps.
No, there's stoic in